Well, it is a pleasure to introduce Eder, Leandro Sanchez, Quiceno, who will talk about links of mixed singularities. Thank you very much, Eder, for accepting the invitation. You can start when you are ready.
Oh, thank you. First of all, I would like to thank the organizer of the Brazilian Singularity Theory webinar. It's a great pleasure for me to present my work here. Yeah. Today I will talk about links, particularly for associated to mixed singularities. Right. The almost results that I will talk today is a joint work with Raimundo Nonato and Benjamin Bob. Right. Well, the talk is divided in these three parts. Right. We talk about the introduction, the main inspiration of our work, and the second part I will talk about mixed polynomial. And the last part I will talk about topological description of the link associated to mixed polynomials. Right. Well, in the introduction, I will consider real polynomial mappings from R4 to R2. This is because the associated link of F that we will talk later is the classical links embedded of circles in the S3 sphere, right? We consider that F of 0 is equal to 0. That means that 0 belongs to the zero set of F. And we will consider these two sets as a jet of set on the origin, right? The first one is the zero set that we will talk about variety of F. And this is the zero set of F as a jet of set. And the second one is the singular set of F, that is sigma F. This is the point R4 such that the Jacobian matrix has no maximal rank, right? This is the singular set for us. And for the case of real mappings, we have these two types of isolated singularity on the origin. The first one is the weakly isolated singularity. That means the intersection between the singular set sigma F and the zero set of F is just the origin as a set of as a jet of sets, right? And the second one is in the particular case when the singular set is just the origin, right? And in this case, we say that it's a isolated singularity and the origin, right? And by words from Milnor, right, we have that the intersection of the variety with small spheres centered on the origin, denoted by S3 rho, a small enough rho. We have that the intersection give us a submanifold of the S3 rho, right? That we denote by LF, right? And is this LF for us case and the R4 to R2 is a classical link, right? Well, this is what means a link of the singularity, right? These links can be called in particular way. We will call a link L in S3 is to be weakly algebraic or real algebraic if these two things happen. The first one is that there exists a polynomial map from R4 to R2, well, when 0 equals 0, and such that FL has a weakly isolated and respectively isolated singularity, right? And the second point is that there exists a radius, rho 0, and such that for every rho small or equal to rho 0, the link that is defined by the intersection of the zero set of FL and the small sphere is isotopic to L, right? That is this small sphere has diffeomorphic to S3, the common, the usual S3, right? And these two things, these two defined links are important for us because we can associate the topology of the link with polynomial maps, right? And for this case, when you have a weakly algebraic link, we call this FL a weak realization of the link, right? And respectively, a strong realization of the link, okay? Then this is an interesting problem that to know for given a link L, it's interesting to know if there exists such a weak realization or a strong realization, okay? Well, for that, we have a first answer about this problem of the weakly algebraic links given by Akubulu and King, and also recently by both that if a different proof, we have that all links are weakly algebraic. That means for any link on the sphere, tree sphere, there exists a weak realization for this link, okay? Well, for the case of real algebraic link is a little bit more difficult because we have to prove that this weak realization that in the case before, the theorem before, has actually isolated singularity, and this condition is not so easy to prove, right? But we have a characteristic of these real algebraic links, and is given by the results by Milnor. Using Milnor, we have that real algebraic links are fiber links, okay? That means the complement of the link on the sphere is a bundle of some vibration, okay? A locally trivial vibration, okay? And we have a conjecture about this, the reciprocal of this result that is given by Benedetti and Sciotta, and say that, in fact, all fiber links are real algebraic. This is the main problem that we want to work on, right? And I have a table of strong realization or links that we can find in the literature. And well, just to point out the works about the conjectures, just to mention a little bit, the Brenner results is just to characterization of links of complex curves, right? That means the zero set of holomorphic polynomials in two variables, right? That is well known in the literature of complex singularity, right? This is called the union of iteratory nodes, okay? We also can find different constructions of links and the literature that we can perform a strong realization of these links, okay? Well, actually, in the recent works, we can find that these strong realizations can be described as mixed polynomials, right? And then mixed polynomials show as a nice, how to say that, show as a nice polynomials to work with the conjecture, right? I mean, I will talk about the definition of mixed polynomial, but I want to say that mixed polynomials is a nice object to work with, to try to solve the conjecture, right? And then it's because this is the reason why we work with mixed polynomials instance of real polynomials maps. I mean, we will see. I will explain that in a moment. Well, but we have two problems here. The first one involves with the conjecture. The first one is that we need sufficient conditions to get a weakly isolated singularity or isolated singularity, right? And this isolated singularity is a condition that is not so trivial to prove. Then we want to work in such a way that we can get a sufficient condition that simplify this difficulty. And the second problem is that can we describe the link type LF of a polynomial map with a weakly isolated singularity? I mean, by the Milner result, you know that there exists some rule zero in such way that for any row small or equal to this rule zero, the link type does not change. But we don't know how small enough this row zero have to be taken. And then the link of the singularity is not so easy to read in some way. I mean, to plot in some software or something like this, because we don't know how small is the link. Then we need a different techniques in order to try to read or plot the link type of the singularity, right? And this is the two problems that I want to say something, not to solve at all, but to say something in some classes of polynomials, okay? This is the object of the talk. Well, as I say, the results here, this talk, we can find in this preprint, right? And this also that this work was supported by FAPESP, right? Okay. What means by mixed polynomials? Well, mixed polynomial is a complex polynomial in two variables. Okay, we call u and v. It is a complex polynomial, and these two variables, and also in the conjugate of these variables. Okay, and okay, again, we are interested in the behavior around the origin. Then it's interesting to we have to put the origin equals 0. Is that where the origin belongs in the variety of the F, right? And the other point here is that this is a way that we can use to represent a polynomial map from R4 to R2, right? It's just to notice that F can be seen like the two polynomials, real polynomials, given by the real part of F and the imaginary part of F. Well, and why we can use that? Because it's more simple to describe the link type also, and also we can give a different ways to define the singular set, for instance, of F or of the real polynomial map as a mixed polynomial. We can see. Let me explain this in this definition. Well, the singular set that we defined before, like in this way, the Jacobian has no maximal rank, can be seen in terms of mixed polynomials and partial derivatives of these mixed polynomials. That means partial derivative in variable u and the conjugates. Okay, and we can prove that. We can prove that the singular sets can be simplified as the zero set of these three mixed polynomials. Right? This way of to see these real polynomial maps can be help us a lot. We will see later. Okay. Well, the other important thing that why we work with mixed polynomials is that we can define a Newton boundary associated to the mixed polynomials of the radial degree. We will talk about, but this is a Newton polygon associated a mixed polynomials itself, not just the real polynomials maps as mixed polynomials. Okay, and this Newton boundary is very useful for our description of the link. Okay, and also to the conditions, sufficient conditions to get a weakly isolated singularity or isolated singularity. Okay, then the construction of the Newton polygon of this mixed polynomial is given in this way. You have you consider a mixed polynomial f c bar. This notation is not so helpful, but we denote as in this way because maybe fz maybe have confusion with a holomorphic polynomial itself. This is to notice that f has some monomials with conjugates of z, but f is just a polynomial in 2 variables, right? Not 4 variables. Okay. Well, the Newton boundary is the compound boundary of the convex hull of this support. The support for these mixed polynomials in 2 variables is defined by the sum of the sum. In the first coordinate, you take the sum of the degree of the u of the component of u plus the degree of the u bar, right? This means by the first coordinate of the support, and the second coordinate of the support is the degree in variable v plus the degree in variable v bar. Then in such way, the Newton boundary is related not just for individual variables, just the sum of the variables when they're conjugate way. Then this is the reason why you have to combine this to the conjugate and the variable itself, and then you get in this case you get just 1 Newton polygon in 2-dimensional. Okay. Well, even in this case that we work with 2 variables, I mean, the mixed polynomials itself are a polynomial map in 4 variables, but using the supports, we can see a polygon, a Newton polygon in 2 variables. I mean, not in 2 variables itself, but in the radial way that they change it. But a different way to define a Newton polygon associated to the mixed polynomial of the real polynomial mapping is just to say in the usual way, but in this case we have a high dimensional Newton polyhedron because you have to involve the degrees in each variables separately, not just to put together. Okay. This is also a nice thing to work with mixed polynomials, that we can simplify the Newton polyhedron in this way. Okay. And now we will talk about the the natural objects involving with Newton polyhedras, that is the phase functions, the degrees, and also the Newton principal pairs, and the way how we can define the phase functions of the Newton polygon is in this way. You have to select a wave vector. This is a pair of positive natural numbers, and we associate the phase functions, the phases of the Newton boundary, right? That we denote by the delta Q. And this delta Q is defined by the phase on the Newton boundary, such that this linear mapping LQ takes a minimal value. This minimal value is defined by dQf, that because this minimal value depends on Q, right? And the restriction of F on this boundary, this phase, give us the phase function, right? FQ, right? That is the sum of these monomials that satisfies that the sum of these degrees belongs in this phase, right? And for instance, in this example, we have 5 phases. 3 phases of 0-dimensional phases that we call vertices, that we can select. We can see here in 0, 7, and 4, 0, for instance, and this vertex that we will call no strength. Okay, here we have 2 one-phases, one-dimensional phases that is given here and here, right? I will talk, and then associated to these 5 phases, we have 5 phase functions. Okay. The other thing that is important here that we can define is the Newton principal pair. What means Newton principal pair is the restriction of F on the boundary itself. Okay, it's just to give the sum of the monomial that the sum of the degrees belongs on the boundary. Right. This is the phase Newton principal pair. Right. Well, this is a technically thing except that we will use later, but for each phase function, we can associate a one wave vector, right? In such way that the phase function associated to the LP1 is the phase. Well, we want to order the set of wave vectors that associated to one phases, just one phases, no vertices, right? For instance, in this example, we want to take 2 wave vectors associated to the one phases, right? And then we want to order in these sets using these rules, comparing the quotient between the first coordinate and the second coordinate, right? And then we have a order set of P. Okay, and the other important thing that we can do with the phase functions is this follow. For any P1 in this P, we can define a set of functions defining in C times S1, right, to C, and such that CJE is equal to this this form using the phase function associated to P1. Okay, when this element is the degree of S respect P1, this Pi2 means the second coordinate of the wave vector, and this Chi is the quotient of P1 and Pi2, right? And R means the radius or the module of the second variable V, and T is the argument of V. Then we can define this Ji in this way, okay? And we notice that this Gi does not depend on R, okay? The Gi is very important to make the descriptions of the link of the singularities, okay? Just I will return on this Gi later, okay? But is just to point out that we can make this kind of definition of Gi using the phase functions. Okay? Well, the first problem is that we want to give sufficient conditions in order to get a weakly isolated singularity or isolated singularity. Okay. Well, we take inspiration for the works of Oka and Mondo in order to give a sufficient conditions to get that. Well, the definitions is quite technically, but we will see that. We say that F has a Newton inner non-degenerated boundary that we denote by I and D if both of these conditions hold, okay? The first one is that the phase functions fp1 and fpn have no critical points in these sets. It's not, this set is a subset of C2, right? And this also V, fpn, intersection with this for the pn thing. Remember, p1 and pn are the first wave vector in the set or ordering the ordering sets of wave vectors associated to one phases. Remember, one phases. This is the first one and the last one in this set. And the second condition is the following. For each one phase, and no extreme vertex, just no extreme vertex. No, this does not involve the extreme vertex. The phase functions or the restriction of F of these phases has no critical points in these sets. V, F, delta, intersection with D star 2, where C star 2 means C minus 0 squared, right? Well, why? Now I will explain why is the inspiration from Oka, right? This second condition, IND2, for every phase, I mean, if we change one phase in no stream, include a stream vertex, these two conditions is the same of the Oka's definition of non-degeneracy, okay? This is why these are inspiration, okay? And we denote this non-degeneracy by Oka by ND, non-degeneracy, okay? Oka's definition is a generalization of Koshnirenko's definition for holomorphic polynomial into variables, right? Or even in high dimensional, but for our case, that is C2 to C is the Koshnirenko definition. And also, our definition is the inner non-degeneracy is a generalization of Monda's definitions that involve the first condition, right? Now, this is a Newton inner non-degeneracy condition, but we can do that in a strong way. We can ask a little bit more on this in this I and II, and we can define a strong notion of non-degeneracy. And we say that F has a strong Newton inner non-degeneracy boundary that we denote by as S, I, and D. If these two things holds, it's the same way that FP1 and FPN has no critical point in C2 minus V equals 0 and C2 minus U equals 0 respectively. Notice that the strong condition does not involve the variety of F. We ask for a little bit more. We ask for these two sets, all these two sets. Okay? And the second condition is analogous before, but the critical has no critical points in C star 2. Okay, and then we have this result that is some advance in the problem 1, the theorem in 2.2. If F is a strong inner non-degenerated, respectively inner non-degenerated, and then F has isolated singularity, respectively weakly isolated singularity in the origin. Then these two conditions that are conditions on the boundary of the F give us some results in isolated singularity or weakly isolated singularity. When we can see in this diagram how our condition generalize the OCA conditions that OCA proof that in the case of the diagram of the Newton boundary, was convenient. That means the Newton boundary intersect both axes, and also a strong non-degenerated condition by OCA. That is just to ask for the second condition or inner non-degenerated to include the extreme vertex. Then he proved it that we get isolated singularity and weakly isolated singularity respectively, right? But our conditions generalize in such a way that we include this polynomial that does not convenient, and also we include some this polynomial that is not degenerate in the sense of OCA sense, right? And this is a generalization, right? Okay. For now, we want to ask the second problem, that how to describe the link of the mixed polynomial when we have some of these two sufficient conditions, right? This is the proposed here. Well, for that, we need to define the topological object here that we will work. Then this part is just to define the notations or the definitions of links and a little bit more, and breaks actually, but we will explain a little bit more, the connection between breaks and links. But now we need the notion of nested break. Okay. Well, we will consider a sequence of geometric breaks. We know B1, B2, Bn. Each break has S1 strength. Okay. And what means by geometric break? Okay, geometric break are a disjunct union of strengths. Okay, on the C times 0 to P, in such way that they are disjunct also, and the intersection when the level sets are constant. I mean, these strengths are transversal to each level set, and also the initial points, that mean z 0 0 coincide when some endpoint ci j to p, right? This is the idea, a short idea of nest or geometric braid, okay? And in this sequence, we ask for a little bit more. We ask for in the B2, B3, Bn does not intersect this zero line, 0 times 0 to p. This is the condition here. Bi does not intersect this zero line for any I different to 1. We allow that B1 intersect this line, okay? And the nested braid is defined in this iterated way, okay? For this zero line, we take a teeny cylinder, solid cylinder around this zero line in such way that this cylinder does not intersect the strengths of B2, okay? Then we embed this tube in B1, right? In such way that we don't have twist of this tube, right? We just to put in this tube, right? And we get a B1, B2, that is this union of this B1, B2 is in this way, right? And then we make the same procedure as before. We take a teeny solid cylinder around this zero line in such way does not intersect B3. Then we put, without twist, this cylinder, solid cylinder inside. We embed this tube inside, and we get B, B1, B2, B3. Okay, and it's in this way when you have making this for any Bn, Bi to Bn. Okay, we get that. But formally, we can define this B1, B2, Bn is in this way, adding some epsilon chi, where epsilon is small enough, ki is a sequence of decreasing interior numbers. Okay, but geometrically, we can describe in the way that I say. Okay, this nested braid B0. Let me to put here. B0 is just the same is the union of B, B1, B2, Bn, but you add this component, right? We have to add something like this here around or some of the last two. Okay? And this we will call that B0 in some component here. Okay, now we will see the result of the description. Okay, well, now we need to associate to a mixed polynomial f some braids in such way. Then we will see that in this way. Now, let f a mixed polynomial, and we take that the principal part is USM holomorphic. What this means, the principal part is USM holomorphic. The principal part, F gamma, does not depend on U bar. The monomials of this polynomial, the monomials does not have a U bar form. And we ask that the F has a Newton inner non-degeneracy boundary, okay? Then we define big one as a the zero set of G1, where Gi is associated to FP1 in the as in the question 2. Remember that we count this kind of decomposition using FP1. Okay, and Bi is just is defined as the intersection of the zero set of Gi with this C star times 0 to P. Okay, then we have this description of the link of the mixed polynomial in a non-degenerated boundary. When under the above conditions, this mixed polynomial f has weakly isolated singularity. This is because it has a Newtonian non-degenerated boundary, right? This part, and the link of f is isotopic to the closure of the braid B, B1, B2, Bn, where each Bi is associated to the phase function Fpi. Okay, and this is if f is U convenient. What it means for U convenient? The axis in the Newton boundary associated to the components U intersect this axis. If in the case that the Newton boundary does not intersect this, we will call not U convenient, right? And in the case that f is not U convenient, we have that the link is isotopic to the closure of the B0, B1, B2, Bn. Okay, and notice that the link of f is described by the information on the Newton boundary, on the Newton phases. Okay, in particular, the link of f does not depend on monomials above the Newton boundary. Okay, then we have this result that the link of these mixed polynomials are isotopic, is isotopic to the link of the Newton principal pair. Okay, this is a consequence of this description. Okay, I think that I didn't have time enough, but in order to generalize this result, the result before, to the case where the Newton principal pair is mixed, I mean, is not U semilomorphic anymore. That means that the phase function can be involved all of the variables in the conjugate. We have to include a new condition in the non-extreme vertex, but I have to. I don't have time enough to talk about this, but I will show you that we can generalize these results, this theorem, in order to include a more general mixed polynomial. Okay, and the link of the singularity is not more a closure of braids, but now we can involve links itself, right? That this is the case L2. This is important to notice that for the general case, the GI involves U and U bar. Okay, then we cannot apply the fundamental theorem of algebra in order to guarantee that the zero set we have the full rods, possible rods. Okay, then the number of rods when you vary T can be changed because you involve U and U bar. Okay, then the description of the links of the zero set of GI can be empty for some T. Then the zero set of VGI looks like this L2. Okay, then but the other things happens analogy to the last case. We have a nested link instead of nested break, okay? And the procedure is just to put use solid torus instead of solid cylinders, and you have to embed these solid torus in a teeny neighborhood of this core that we call alpha, and we can make this procedure iterated in order to define this nested link, okay? And we have this result that if we include the nice condition, then the link of F is isotopic to the nested link. Again, the L1, L2, Ln are associated to the phase functions, okay? Then, again, in particular, the link of F is isotopic to the link associated to the Newton principal part. Well, how many time I have?
Eder,
See?
you can hear me? You have 5 minutes.
Okay, just to conclude the results, I put this example. Just I put fast in this. I will throw this example fast. Well, you take F. In this case, I take holomorphic, but you can take a mixed polynomial instead. But you draw the support of F, that is these 3 points, and then you take the Newton polyhedra and the Newton boundary. Okay, this Newton boundary is convenient. F is convenient, right? Because intersect both axes. Okay, and well, it's convenient. Is not degenerate in the sense of Ockham says sense, and that this is a generalization of Cauchy-Nerenko sense. Okay, and also we have that F has isolated singularity. This is because the non-degeneracy and the strong non-degeneracy on the complex case are the same. And this result is well known. You don't need to apply our result, but using just last results by Fukui, Yoshinaga, and Kim, that the link of F is isotopic to the link of the Newton principal part. But we can see our result as a generalization of the result by Fukui, Yoshinaga, and Kim in order to include the mixed polynomials and non-degeneracy conditions. Okay, and well, here we can see that the principal part of F is U squared plus V3. Okay, then we have that F gamma is equal to this, and this coincides with the phase function of F related to this weight vector, right? And for the description that we made before, we have to see V, the polar coordinates of V, and that means that R is the module of V and T is the argument of V. And then we can perform this decomposition. So this define this G in this way, where 6 is the degree associated with 1 of F. And this 3 is the P1, and 2 is P2 prime. G is equal to U squared plus E3IT, okay? Then the zero set of G, we can see G, okay, here, again, we can see G as a T parameter, okay, of a family of univariated complex polynomial, I mean, in one variable U, right? And then we can see the zero set of G like in this space C times 0 to P, where each level is T. And we can see that the zero set looks like this, okay? And notice that this is a representation of the zero set of G, but G is a function from C times S1. That means in the full solid torus, C times S1, right? That the best way to represent the zero set of G is just in a solid torus, okay? This represents C for us represents something like C times S1, okay, or a disk times S1, okay. And we notice that J minus 1 looks like this. In fact, is a link on this solid torus. But we can prove that the link associated to the F gamma is isotopic to this zero set of G, okay. This is the relation between, for us case, this is the relation of the zero set for these phase functions with the zero set of dg using this decomposition, okay? Then the answer for us is the link of the original F applying our result is the 3-4 knot, that is the zero set of this G, okay? This is the description that we can make for the these polynomials with nice inner non-degeneracy boundary. Okay, the answer that we give for the first problem was that the E and D implies weakly isolated, S I and D implies isolated singularity. And the second problem that we can we describe or read the link type of F for this weakly isolated singularity? In the particular case that satisfies I and D. We gave that for a nice I and D boundary, LF is isotopic to this nested link, okay? That is constructed from the information of the phase function, okay? Okay, and this comment is actually important, that the topology of Li depends on the Newton in the phase, but also depends on the coefficients. If you change the coefficients of these monomials, the link type can be changed. Okay, does not depend on the point itself. It depends also on the coefficients of the phase function. And the second point that why this nice condition is important is that if we remove in the nice condition, the link is not a nested link anymore in general. And we suspect that this result that adding some monomials above it can be changed the topology. That means the Yoshinaga, Fukui, King analog results in this case can not be true. Okay, maybe this nice condition is necessary to get a nested link, and this result of the link of F is isotopic to the Newton link of the Newton principal part. And that's all. Thank you so much.